today we're gonna do the dropout and batch normalization of the Intro to Deep Learning course. Okay, let's go. In this exercise, you'll add dropout to the Spotify model from exercise 4 and see how batch normalization can let you successfully train models on difficult datasets. Run the next cell to get started. Okay. Run it. Now, like normal, this will take, like, years, so... Okay, I'll let you know when it's done. Okay, it's done. First load the Spotify dataset. Okay, more loading. There's always a bunch of setups, so. Oh gosh, I don't know what all of this does. Okay, I don't know what that is. Here is the last model from exercise. What? Okay, I read it right. From exercise 4, add 2 dropout layers, one after the dense layer with 128 units and one after the dense layer with 64 units. Set the dropout rate on both to 0.3. Okay. Okay, do they want the layer like after like this? Or do they want it like to apply it to the layer itself? Okay, whatever, screw it. I'm gonna do both, because. One there, and one here. I should also probably add the S here. Okay, so it was the one after. Okay. Now run this next model. What? Okay, no, I'm reading too fast. Now run this next cell to train the model to see the effect of adding dropout. Eh? Is it going? Okay, it went. Oh, that's cool. Yeah, okay. Recall from exercise 4 that this model tended to overfit the data around epoch 5. Did adding dropout seem to help prevent overfitting this time? Where's epoch 5? Is this the epoch? I forgot. If this, yeah, this should be epoch 5. I think so, because it's less noisy, right? Oh yeah, from the learning curves you can see that validation loss remains near a constant minimum even though the training loss continues to decrease, so we can see that adding dropout did prevent overfitting this time. Moreover, by making it harder for the network to fit spurious patterns, dropout may have encouraged the network to seek out more of the true patterns, possibly improving the validation loss sum as well. Sum? I think it's meant to be SUM? Or am I just dumb? Okay, whatever. I'm not supposed to be learning about grammar. Now we'll switch topics to how batch normalization can fix problems in training. Load the concrete dataset. We won't do any standardization this time. Okay. This will make the effect of batch normalization much more apparent. Okay, I just run it. I don't know what I was thinking. Did it run? Okay. Run the following code cell to train the network on the unstandardized concrete data. Unstandardized. Oh, please don't take 10 years. Okay, it won't take 10 years. We're good. Oh yeah, did you end up with a blank graph? Trying to train this network on a dataset will usually fail. Even when it does converge due to unlucky weight initialization, it tends to converge a very large number. Okay, so we don't have a graph. Batch normalization can help correct problems like this. Add 4 batch normalization layers, one before each of the dense layers. Remember to move the input shape argument to the new first layer. Oh my gosh. So layers batch normalization, comma, input shape, input shape. So we don't need this anymore. We do need the parentheses. You know what? I'm lazy. I'm not gonna just boom, and then boom, and then boom. This should work. Yeah. Okay, run the next cell to see if batch normalization will let us train the model. I thought it was finished. Don't take 10 years. Hello? Okay. I don't know what happened here. Did adding batch normalization help? What was it supposed to do? Oh, it will if it let us train the model. Yeah, it lets us train the model. You can see that adding batch normalization was a big improvement on the first attempt. By adaptively scaling the data as it passes through the network, batch normalization can let you train models on difficult data sets. And that's the end. That's also another short one. That's great. So we finished this one. I hope you all have a great day, and I'll see you in the next one. Bye!